So another way we can describe a line is with something called parametric equations, which you've probably studied in Calculus 2. Right? This is where we describe the x-coordinate and the y-coordinate as functions of t. Right? Well, this r of t here really is just x, y, z. So using this equation here, we can get, so we add these two, and we have x naught plus ta, y naught plus tb, z naught plus tc. Right? And then if we just break up this vector notation and set the first coordinates equal to each other, the second, and then the third, what we get are called the parametric equations. Right? And that's just going to be writing out the three of these. T looks a little nicer at the back anyway. Okay, so we've talked about two different ways to write down a line. We had the vector equation, and we had these parametric equations here. Both of those involved an extra variable, though, this t, right? Which, if you like, you can think of as kind of a time parameter for how long you've walked along the line. But back in graphing things in two-dimensional space, the xy plane, we always had a nice equation, ax plus by equals c, which describes the equation just using the variables for the plane, just the x and the y. There's no t. Right? Can we get a similar thing here for lines in 3D space? Well, we can. Right? So there's this extra t. Well, I shouldn't say extra. There's a t in each of these, and that's something they all have in common. So let's solve for t. So say in this first equation, what we can do is move this x naught over, and we'll have x naught, sorry, not x naught, x minus x naught equals at. Right? And now we can divide by a and get t is x minus x naught over a. All right, we do have to be a little careful when we do this, though. We have divided by a. So we put a little warning in here that a had better not be 0. Right? You guys don't want to divide by 0, you'll explode the universe. I'm sure you've seen many pictures of people dividing by 0 and giant holes in the ground, for example. All right, so we're going to do the same thing to either of these as well. And that'll give us t is y minus y naught over b, and t is z minus z naught over c. And these likewise come with the warning that b had better not be 0, and c had better not be 0. Okay? So assuming now we're in the case where a, b, and c are not 0, we have these three equations here, and they're all equal to t. So what does that mean we can do? Well, what it means we can do is say t is equal to, well, from the first equation, x minus x naught over a, but t is also equal to y minus y naught over b. So we can just continue the string. And one more time with the z's, z minus z naught over c. Right? So this here, these are known as the symmetric equations. So again, we see the same thing here. We have the point x naught, y naught, z naught, which is that's some point on the line. And then we have the direction vector showing up in here. The I component goes under the x's, the j component goes under the y's, the c component goes under the z's. Okay, so you might ask yourself, well, what if one of the a, b, or c is 0? Well, that's actually not so hard to deal with. And since all the cases of that happening are fairly similar, let's just look at what happens if, say, C is 0. Okay. So for example, if C is 0, if it is 0, then what does this Z equation here look like? Well, it's just Z equals Z naught, right? Well, if that's the case, then we can't have this term being in here, this Z minus Z naught over C, because, well, then the universe has exploded because we divided by 0. So what we actually do is just kind of take what's left of this and add this onto it, right? So we would get x minus x naught over A equals y minus y naught over B, and then we just add on this piece. Z equals Z naught. Okay? So that's what would happen if one of them is 0. If two of them are 0, then, well, actually, we would only need the leftovers of whichever two have the 0. So let's do another little thing here. Put this in the corner. This doesn't happen very often, so we'll just put it in the corner here. Let's say if also B is 0, then we get y equals y naught and z equals z naught. And that's actually all we need. Because if x is the only thing that's allowed to change, then if we say what y has to be and what z has to be, letting just one variable change will give us the entire line. So think of graphing something in the xy plane like, x equals 2, for example, right? When x equals 2, actually, let's do a little sketch of that. Here's y and x. If we graphed x equals 2, well, we would have 1, 2, and then we get this vertical line here. Right? So this is the line x equals 2. And as you see, x is fixed at 2, y can be anything. Right? In 3D space, it'll be the similar kind of thing, except now you'll have a z-axis. So actually, let's see if we can figure out how to graph, let's say, y equals 1, z equals 2, just as a quick little example here. So remember, we have to use our right-hand rule to decide what these look like, or how to label these axes. So since x is going out, if I curl towards y, now we're going to pick y to be that direction, so z is up. Or maybe I can just start by saying I want z to go up. So where does x and y have to be? X has to be going out, y has to be this direction. Okay. All right. So if we specify that y is 1 and z is 2, well then, y is 1, z is 2. So there's one point, and the actual line then is just going to be parallel to the x-axis, because x is the only thing that can change here. Okay. So this is the line, those equations.